This is going to be our second video in our series about material balance and process control dynamics. In this video will be a direct continuation of the previous, in which we looked at a three-tank system and described the change in height as a result of a change in time due to uh, the inflow and outflow, as well as flow between each tank going on in the factory that we've created. Now, in Python, we're going to be modeling this behavior, these differential equations, using the SciPy optimize solve IVP function in order to turn that change in height over a change in time differential equation into an equation of height in terms of time, and then use the Plotly plotting library in order to plot those as a graph over time, and eventually see what state our system will end up in given initial conditions that were written out for us by Carlos. So to get started, just like with any coding, first we're going to import, oh, import numpy as np. That's always what we do. Next, we're going to from plotly dot plotly dot subplots. I spelled that wrong. Subplots. We are going to import make underscore subplots. Then we're going to, again, for my personal taste, we are going to from plotly.io, we are going to import, I believe it is, let's see, plotly underscore, no, it's plotly underscore template. Oh no, it's just importing plotly.io. That was the mistake. Subplots. Enter. Import plotly.io as PIO. Simple. And then we go through and do PIO dot templates dot default. And we're going to set that equal to plotly underscore dark. And then finally, we're going to import the equation that's going to be helping us turn those differential equations into a straightforward equation of height in terms of time, which is going to be from SciPy dot optimize. We're going to import solve IVP. So that's all we're going to need. Cannot import it due to dependencies. Solve IVP from IP optimize. Solve, yeah, no, that definitely should work. I don't know why it's giving me an error here, but oh, it's because it's not SciPy optimize, it's SciPy integrate. Silly. And I spelled integrate wrong. Integrate. There we go. Now it stopped complaining. Perfect. So now that we have our solve IVP from SciPy integrate, not from SciPy optimize, good thing I caught that, or at least Python caught that and told me, we're just going to get right into modeling the differential equations that we derived in our previous video into Python. So we're going to define a new function, and we're going to call it diff eq, because differential equations. And obviously it's going to return something like so. So, what are we actually going to import into our differential equations function? Well, because of the way that solve IVP works, the first variable in our function that we plug into it, any function that's plugged into IVP, must have t for time as the first variable. Whether or not anything in the actual differential equation depends on time, because solve IVP is constructed as a function in a way that needs to be able to account for an equation that includes time in the differential equation directly. All differential equations put into solve IVP have to have t as the first thing. So we're going to have t, and then since it's a vector of multiple differential equations coming out, we're going to want a vector going in. Now, since we're solving for three differential equations, one to model each tank, we're going to have in our equation h1, h2, and h3. We're going to unpack that from our vector we're importing, so that way we have all three of these variables that we can work with. Now, As far as modeling the differential equations, we wrote those differential equations, if you'll remember, in terms of the flows. So instead of just writing everything out right here directly in the return, we're going to do a little bit of work ahead of time to make the return lines look a little bit nicer. So we're going to do Q in is equal to, we have Q from 1 to 2 is equal to, Q from 2 to 3 is equal to, and then Q out is equal to. So that's easy. That'll be pretty nice to handle. So Q in. As we remember, Q in, which I'll probably pull up the previous work from our last video up on the screen right now. It'll slowly fade in. You'll see another handsome version of past me from earlier today, pointing at them quite nicely, hopefully, or maybe just turning my back to the camera, who knows. So we know that we discussed that because we're talking about a proportional controller, where the flow into the tank system is going to be dependent on the difference between the set point, the point we want our preferred tank 3 to be at, and the actual height of tank 3, and then obviously some constant in order to regulate that. That's what a proportional controller means. Our Q in is going to be Kc times, and then that difference we talked about, so I called that set point 3. So I'm going to write that as, make that variable S3 minus, and we're going to have H3 right there. So that's going to be our Q in. Similarly, or not similarly, because it's not proportionally controlled. This is just due to the way that it works. We said that we were going to have the flow proportionality constant, which I'll call alpha 1, 2, times, and remember we had the difference in heights, which would be, in this case, h1 minus h2, because again, we defined flow to the right from tank 1 to 2 and tank 2 to 3 as positive flow. So we're going to have the difference in those written like that, to the power of 0.5, because remember, again, that's the square root for flow. And remember that in this case, we'd want to make sure that if this roundup is negative, because again, if this roundup is negative, it wouldn't work because we'd have a negative number inside of a square root, because remember to the 1/2 power is the same thing as having a square root. That this wouldn't actually work because it's be an imaginary number, and we don't have an imaginary value. It just means that the flow would be going the opposite direction. So instead of putting that in parentheses, or in part of putting them in parentheses because of the way it works, we're going to do np dot abs, right? Yes, absolute. And we're going to wrap this in the absolute value function so that it takes the absolute value of this. And now because of that, if we want to indicate the direction of flow, we're going to have to do that in front of our flow, and we're going to have to do the np sign function, which again tells us the sign, np sign of whatever we're multiplying. So again, since when h1 and h2 is negative, that means we're flowing backwards. We're just going to do the same thing, h1 minus h2 here. So this says when h1 is less than h2, obviously this will be negative, so this np sign will output a -1 and make sure to indicate that our flow is going backwards from tank 2 to tank 1. So this is our equation. And for tank 2 and 3, it is basically exactly the same, except all the tank 1s turn into tank 2s, and all the tank 2s turn into tank 3s, because again, we're talking about the flow from 2 to 3, and alpha 1, 2 becomes alpha 2, 3. That's our only difference between the two of them. Now, Q out is very similar, except remember that the tank 4 that it would be flowing into is actually outside of the system, which is why we call it Q out instead of Q34. Now, because it's flowing out, there is no difference in flow, because the external height, for example, the height of the environment per se, would always be 0. So there is never going to be a reverse flow flowing into tank 3 through the tank, the Q out pipe, the outward flow pipe. So we can simply write this as alpha, we'll call this alpha 3, times the height of tank 3. So h3 to the power of 1/2. So here we have all 4 of our flows defined. Now that we'll let our image of our previous one fade out, and we'll jump to another image of our previous video where we actually show the differential equations, because this again just models the flow of our differential, the flow of our volume between our tanks and in and out of our system. So what we actually need to model is the change in height over time in terms of those flows, which are then in terms of the height. So we remember that I'll just put this in comments here. These are all in terms of dH over dt is equal to, because again, we isolated everything for dH over dt when we did that on the chalkboard, and looking off of our work from our previous video, we know that the equation for the height of tank 1 over time is negative Q12, the flow from tank 1 to tank 2, because this is from the tank 1's perspective. A positive flow would indicate a flow out of tank 1, which would decrease the volume, and that's just going to be divided by A1, which is going to be the cross-sectional area of tank 1. Now similarly, tank 2 is going to be, we have to wrap this in a smaller layer of parentheses because there's an addition and subtraction, is going to be Q12 flowing in, plus we also have Q in, which is flowing into tank 2, minus Q23. Again, any volume flowing out of tank 2 into tank 3 as long as Q23 is positive. And all of that is going to be divided by the cross-sectional area of tank number 2, because again, this describes the change in the volume, and the change in the volume divided by the constant cross-sectional area will give us the change in height. And finally, I don't know what that just did, but I don't like it. There we go. Finally, our change in height in tank 3 is going to be equal to the flow in and out of tank 3 divided by the cross-sectional area of tank 3. So the flow in and out of tank 3 is going to be Q23, flow from tank 2 into tank 3, minus Q out, which is the flow out of tank 3 into the surrounding environment, which has a height of 0, which is why we'll never have to worry about the sign going backwards. Finally, dividing that by A3. No, not at least 3D. And then we can close these parentheses normally. Oh, but I almost did something I did in the previous video series, which is forgetting commas, where they are important. So we're not going to do that. We're going to make sure we have a comma between all of ours. And now, despite the fact that we haven't defined KC, S3, our alphas, or our areas, our cross-sectional areas of our tanks, hopefully this should define correctly, which means we didn't make any formatting errors. Now, right here, we're just going to do our initial, if I can spell it, initial conditions, which are going to be what are all the values that we haven't actually defined within our function yet. So we're going to define our KC. We're going to have to define our alphas, alpha 1, 2, alpha 2, 3, and alpha 3. We're going to have to, no, what is happening? Alpha 3. No, I do not want to rename that. I want to make a new line. I need to set that equal to. And then we're going to have our cross-sectional areas, so A1, A2, and our A3. And of course, we're also going to need the initial starting heights because that's another important part of solve IVP, which we'll cover again when we actually start writing it down and it tells us what we need to fill in. But I'll just write those down now. H0, which is initial height of 1, initial height of 2, and our initial height of tank 3. And that's all the ones we're going to worry about for right this second. But there is one or two more that we'll get to when we actually get around to plugging those into the IVP function. So I have right here Carlos's instructional materials. So just to copy down to make sure I get all the numbers right. So the cross-sectional area is 0.5, 0.1, and 2 meters squared. So cross-sectional area is 0.5, 1 point, comma, 2 point, and I'll put right here meters squared. We also have the initial height is 0.5, 1, and 2 meters. So I'll make sure to put that 0.5, 1 point, 2 point, and then parentheses meters. And we also have a proportionality constant, our alpha, between 1 and 2 and 2 and 3 of 0.1. And then tank 3 draining out has the same proportionality constant. So all three of those are 0.1. So 0.1, comma, 0.1, comma, 0.1. And that's just going to be proportionality constant. Let's write that in there. Constant, right there. that correctly, and our KC, our control, our control valve constant right there is going to be also 0.1. So KC is also going to be equal to 0.1. I'll make sure to put in comments right here, control valve, and I'll put this in quotes, weight, because it's not an actual literal weight like how heavy something is. It is just the weight we're assigning to the difference between our set point and our error. And speaking of our set point, we have to add that as well. So S3 is equal to, what is our set point going to be? We want our third tank to be at 4 meters tall. So we're going to put 4, and then in parentheses, this is going to be, or not parentheses, but in comments, this is going to be in meters. And that is all of our, as double checking to make sure I didn't forget anything. Yes, this is all of our initial conditions that are specified by Carlos. The other things we're going to need we'll get to in a second. So we'll define these, no issues. So now we get into the actual solve IVP portion of our problem. So what we're going to do is we're going to go solve underscore IVP, and we look at what we need. The first thing we're going to need is our function. Then we're going to need our span over which our function is going to evaluate our time. Then we're going to need our y0, which is our initial guesses. And then the other things we're going to need to worry about is our dense output and our method. Our method is just going to say, what kind of what method are we going to use to solve these differential equations, which using, depending on which one we use, will affect how resource intensive it is, like CPU wise, and how fast it will take. But since all of this is being done on a modern computer and not by hand, none of those really matter. So we're going to go with the most accurate one, which is the Rado method. And then dense output, we want that to be true when we write everything in, because dense output will mean that included in our answer will be the actual equations, no longer differential equations, but standard height as a function of time equations that represents all three of our tanks, so that way we can get a value for the height at any t besides just t's included in this t-span, or that are specifically chosen as identifying markers by the Rado method. So, as we saw right here, before I clicked out of it on accident, we see that we're going to need our function. Well, our function is just going to be diff eq, so diff eq. Next thing we're going to need is our time span. So our time span is going to be, parentheses, 0 to what we're going to call t end. So I'm going to make sure that we go over here and we add our t end variable, so we can set that to whatever we need it to be when we need it to be. And then the next thing we're going to need is our y0s. It's not showing that, but yep, there we go, y0s. So our y0s are going to be h of 0 for tank 1, h of 0 for tank 2, and our h0 for tank 3. So those are all of our initial heights, right? And then finally, we're going to need our method. So our method, like as I said before, method is going to be equal to, and that's RADAU, Rado. And finally, we're going to need our dense underscore output to be equal to true. So this way, when we run this, it will actually output, in addition, which we'll go into how we select that using our thing after the fact, it will give us our actual equations instead of just saying, yep, we solved it, and then not really getting anything out of it. So our t end, I think we're going to do around 300 seconds. So I'll make sure to put this in parentheses seconds right there. So hopefully, if we run this, it should solve these three differential equations as I've described them up here. I'm going to case this in parentheses just in case it ends up not liking that. Redefine this to include our t end and run this. And it works. So as we can see here, it's going to give us a lot of stuff. It says, message, it's successfully reached the end of the integration. We see right here this sol part of the answer. This is what I mean. It says it's a SciPy integrate IVP common solution object at some address in memory. So this part of our solution is actually what contains the three functions, the three equations in terms of our three equations in terms of time for the height of each tank. And then here's an example of all the time samples that were deemed relevant. There's the t events right here and the y events, which again, none of that's really important. So what we're going to want to do is we're going to want to take the sol parameter of the object, and we're going to want to dot sol that. And then we're just going to be set that part of the equation equal to sol. There we go. So we redo this. And now we've, again, resolved it for the same thing, but now taken the sol attribute and assigned it to the variable sol. So what do we do with this now? Well, now we need to actually plot it. So I'll just do this in the same window and we'll recompute it a third time, and the wasted RAM will go into Google's pocket because it's not my problem. So what we're going to do is we're going to need to create a new set of x's or time intervals to plug into this solution that we've generated to graph the height of each tank over time, of course needing to feed time into that in order to get out any height at different intervals. So we're going to make we're going to make t plot is going to be equal to np.linspace, which again creates a array of numbers from the start to the stop, which we're just going to do t-end to make sure everything's included that we worry about. And we're going to say we're going to do a big number. How about 501? I always do one more because that makes the way it spaces it out, makes it actually even and usually nice round numbers. So we're going to make a new linear array of a bunch of numbers between 0 and t-end, which is 300 seconds. We're going to make 501. Actually, you know what? We'll bump that up to 1001 just because since it's 300 seconds being covered, doing it 500 is like every 2/3 of a second or every 3/5 of a second or something. So I want a bit more tight coverage, so we're going to go with that. So now that we have our input, how do we actually plug this t-plot into our solution in order to generate our heights at each time? Well, that's actually very easy thanks to the way that solve IVP actually formats the equations. Essentially, since, again, you remember that our differential equation function returns three different differential equations right here. It actually returns three equations in a single sol variable, as we've defined it right here. So what we can actually do is just take sol, which is in itself a function, and take sol of our t-plot, which will run the array of t, our x values, our t's, all of our timestamps, through sol for all three equations, and will actually output an array of each output for each equation. So the way that is basically it would output a 3x1 matrix, and each entry in that matrix would contain a matrix of all of the height values for each tank. So we can just immediately unpack that into our height values for tank 1, our height for tank 2, and our height for tank 3. And again, remembering that because h1, 2, and 3 are defined within this function, they don't exist globally, they only exist within this function, so we can reuse h1, h2, and h3 without it causing any kind of a conflict because these exist outside of the function. So we've generated our plots for each of the height of each of our tank using sol in terms of t-plot, and now all we have to do is actually graph them using our plotly graphing library. So we're going to do as per usual, fig1 is equal to plotly, oh no, we don't have to do that since we already have plotly imported. We just do make underscore subplots. There we go. So now that fig1 hasn't actually been run yet, but it's now generated that subplot, we can do fig1 dot add underscore scatter. And then we're going to make three of these, one for each of the heights. So we're going to do x is equal to our t-plot, which is easy, comma, our y is going to be equal to h1, because again, that's the output of the function, not the differential equation of change in height over change in time, but the actual height in terms of time, height over time equation that we got from our sol. And then we're going to name that. We're just going to call it height 1. And it's going to be in a line automatically, so we don't have to specify that. So we're just going to copy this. We're going to paste it, and we're going to paste it. And all we're going to have to do is change this to height 2, change this to height 2, change this to height 3, and this to height 3. And hopefully, if everything has been done correctly, which looking at it really quickly, it looks like it has. I hope it has. Python will be very angry at me if it's not done correctly, so we're going to see in a second. So we're just going to run this and hopefully see that it's good. And there we go. These are our three plots. So blue and red represent the height of tank 1 and tank 2, which start at their different values, the value of 0.5 and a value at 1. And you see they increase until they overshoot a little bit and hang out somewhere around 4.8. And we see our tank 3, which is the one we had the set point for, which we wanted to end up at 4, actually only gets up to around 2.4. Actually, it's decreasing a little bit as it goes, but it starts picking up again, but it's hanging out around 2.4. So, this is the correct graph. This is what would happen in this situation. The question is, why is it hovering around 2.4, 2.5 instead of at 4? And that's due to the way that proportional controllers work. When you're using a proportional controller, aka adjusting the amount of water going into your system or the amount of fluid going into your system off of its error from the actual value's error from the ideal value, and then multiplying by that some constant, depending on what that constant is, you are never going to reach the actual value, because the closer you get to the actual set point, the smaller your margin of error becomes, and when that smaller number is compounded by being multiplied by a semi-small Kc value, the amount of water it will add in becomes astronomically smaller in proportion to the amount going out. And by that I mean the difference between the amount in net going out. So eventually what you're left with is a steady state system where just as much is flowing in as flowing out. However, you've never actually reached the final set point. So just to prove that, if I change the set point, say, to make it 5 and run it again. Oh, yeah, I did something I shouldn't have right there. It's fine. Run this again. We see that it hangs it at 3.2 again instead of 2.2 for 4. It hangs out at 3.2 for 5. Where if I change this back to 4 and instead increase our control valve's weight, which means how much of an increase in water is it going to give based off of the error, how much of an increase of volume is going to give. We just make that, say, 0.3. That alone will bring it significantly closer. Look, now we're at 3.8 out of 4. However, you can see that as a result, these fluctuate a significant amount more before settling out. And so does this one. It starts by decreasing, then it overshoots 4, or not overshoots 4, but overshoots its steady state, and then ends at 3.3 and slowly increases back up to 3.8. 3.38, not 3.8. And you can tell that as we make Kc closer and closer, or at least a higher and higher number, say at 0.5, you see there's a lot more of a discrepancy here that it really doesn't like. But it's even closer now. It's at 3.6. So as you can see, because we're using a proportional control valve, I'll set this back to 0.1, which is the value Carlos asked us to look at, you can see that there's a significant margin of error between our set point, where we want tank 3 to be, and the actual height of tank 3, which is staying around 2.4 instead of being at 4. So hopefully this teaches you a little bit about the merits of using more advanced control functions for your factories that you'll control in the future as a chemical engineer, or just an engineer in general that's working in process dynamics. And hopefully you'll be able to see that there are better choices than proportional flow control. Definitely. A lot better choices. So keeping that in mind, I wish you the best, and thank you for following along with me on this incredible differential equation material balance process control journey.